Hi-oh! Here we are again. Newton's second law. How force and acceleration relate to each other as well as mass. So first off, let's build the equation. We know from class and we know from the labs that force and acceleration, they're directly related. In other words, as one goes up, the other goes up. As one goes down, the other goes down. So we might say it looks something like, let's see, there we go, like that. They're directly related. Mass, however, is inversely related. We learned this from the lab. We know that when you pull something, if you add mass, it becomes harder to accelerate. So as this goes up, that goes down. So we say they're inversely related. Well, since acceleration is related directly to the force and inversely to the mass, we can put them together. Here we go. Let's build it. Boom! All right, there we go. And now it becomes an actual formula rather than a relationship. This is Newton's second law. We can, of course, do the algebra, rewrite it as F equals ma. However, Newton tended to write it A equals F over m. To really talk about this in some detail, what you need to realize, and this is a key idea, is that we're talking about the net force or the total force. So you might have to subtract some stuff or add some stuff. For example, I push on something and you push in the same direction. Our sum, our total force that we apply would go into the formula. So Newton essentially said, he said, well, the acceleration is inversely proportional to mass and directly to the net force. And we use the Greek letter sigma to represent the net or the total amount. So you may see it written with sigma or you may see it written with the word net. So take a moment and watch Stephen explain a little bit about Newton's second law.
Everybody knows that you can say, if you say anything in hippie speak, it's not true. For instance, like, hey dude, the net force of an object equals its mass times its acceleration, man. There. I completely invalidated Newton's second law of motion. See?
So, what would happen to the acceleration of an object if we suddenly double the force on it without changing the mass? So we just want to see how one thing relates to the other. Well, you can think of an easy way to do this. Think of this as a teeter-totter. Right now it's balanced. If we add something to one side, we either need to take away something from that same side or add the same amount to the other. So in this particular question, we say, what would happen to the acceleration? So we're talking about this thing right here. If we suddenly double the force. So let's do that. Let's double the force. Suddenly the teeter-totter, this side's going to go down. How on earth are we going to balance this? Well, we put a 2 on the left, so we must put a 2 on the right. And since we're asking about the acceleration, that's what we're going to change. See? It's a balanced equation now. Let's try it again, only talking about mass. So here we have our teeter-totter. We say, well, what happens to the acceleration? Same thing as before. If we don't double the force, we're not going to change the force. Without changing the force, we're going to double the mass. So we're not doing anything to the force. How are we going to balance this? Well, there's only one thing we can do. We have to take away from the right side. So it goes, and we have half the acceleration. You see, it's inversely related. As you increase the mass, you decrease the acceleration. One more. If suddenly the net force were to triple, what would happen to the acceleration? You think you know? There you go. It is, of course, the net force equals mass times acceleration. So we triple this. So we must do something to the other side. We must triple that. Well, what about this one? A net force of 50 newtons. We have a little math here. Net force, remember, always write down what you know. 50 newtons. I told you, memorize those formulas, or those units, newtons. You suddenly know it's force. Applied to a mass, that's 5 kilograms. What is the acceleration? Well, I gave the formula in two ways. And there you have it. We're solving for A. Therefore, A equals the net force is 50. The mass is 5. The acceleration must be 10 meters per second per second. There you go. Let's try a little more math. A person pushes with 500 newtons to get his stalled car moving. So we have a force of person 1 pushing. So we got, let's say, a push of 500 newtons. The car has a mass of 800 kilograms and resists the push. So we got force of friction of 100 newtons. What's the net force? You immediately wanted to solve for A, didn't you? The net force. Well, we have 500 pushing one way and 100 pushing the other for a net of 400 newtons. Let's see if you can apply this to a cartoon situation.
Boy, what a night! Mo showed me how to give someone the bum's rush. Here, watch. Get lost, Rummy!
Ah, yes, Detroit style. Very nice.
Finally, if we had a block in space and it has those forces acting on it, what could the block be doing? See, this is actually an application of this Newton's second law, but it's also an idea of inertia. We know the relationship F equals ma. We know that if you want something to accelerate, you have to exert a force, a net force. What's the net force? Yeah, 0. So is it accelerating? No. In other words, this block could be sitting there motionless. It's not accelerating. It could be moving at a constant speed. That's not accelerating. In any direction, just not changing direction. Okay, so it could be at rest, any direction. And there you have it. We'll see you in class.